Alright, so in this video we're going to start talking about astrophysics, and we're going to start off by talking about stars. Now, um, we have a star in our solar system, which we call the Sun, of course, and our Sun is a pretty average star, as stars go. Um, it has a mass of about 2 times 10 to the 30 kilograms, so not too big, not too small, kind of medium star. It has a surface temperature of about 5,800 Kelvin, although as you go in towards the center of the star, the temperature increases. Now, our sun, just like any star, is basically a glowing ball of energy created by nuclear fusion. Okay, and so the way a star is formed is basically stars are formed when gravity pulls together what's called nebula gas. And nebula gas is basically just hydrogen. And so you have a cloud of hydrogen just like floating out there in space. Okay, that could be hydrogen left over from another star. That could just be, hydrogen that's kind of coalesced over time. But over enough time, what happens is the gravitational force of the gas, it starts to pull the gas together. And as the gas gets pulled together, and it gets closer together, the pressure increases, and that causes the temperature of the gas to also increase. And over millions and millions of years, what can happen is the gas can get pulled together until the temperature is such that fusion can occur. And so nuclear fusion is what powers stars. And as we talked about in a past video, it takes a really high temperature to cause that fusion. But once that fusion gets going, the star is basically self-sustaining, and that fusion process is going to cause the hydrogen to fuse into helium. Now, that fusion emits a high amount of energy. We've talked about that in past units. Nuclear fusion releases a lot of energy. And so that outward radiation pressure coming from all that heat, coming from the fusion reactions happening inside the core of the star, basically that creates this giant like outward what's called radiation pressure, and that radiation pressure wants to push the star out and it wants to make it expand, but that force is counteracted by the force of gravity holding the star together. And so in most stars, what we call a main sequence star, the star is in a state of equilibrium, and that equilibrium is reached between the inward pull of the gravitational force and that outward radiation pressure. And again, when I say radiation pressure, really what I'm just talking about is the nuclear fusion producing a lot of heat, and the heat wanting the star to expand, and that outward force is balanced out by the inward force of gravity. And stars can remain in this kind of equilibrium state for billions of years. And then over time, what can happen is as the hydrogen runs out, because hydrogen gets used up in the fusion process, and it gets turned into helium. And so what can happen over millions or billions of years is the star can start to run out of hydrogen. And so once that happens, then stuff starts to change within the star. And we'll talk more about that later. That has to do with stellar evolution. Okay, but over time, the star is losing mass because the mass of the hydrogen has been converted to nuclear energy, and so the star can eventually change. Just to show you some pictures of a nebula, this is one picture of a nebula, and basically what you're looking at is a giant space cloud of, gas, primarily hydrogen, maybe some other elements in there as well. Okay, and this is another one. And so over time, if there is enough mass of hydrogen in a cloud, they can all form together and form a star. Okay, now it's also possible that you might have like a smaller gas cloud that pulls itself together but doesn't generate enough heat to actually start nuclear fusion. And if that happens, then you get what's called a brown dwarf. And a brown dwarf is basically like a failed star. It's like a star that would have been a star except it didn't have enough mass to get started. So it's just kind of like a giant ball of gas, like Jupiter, if Jupiter was a little bit bigger. All right, and so over the next few slides, this basically just kind of outlines the fusion process. It talks about everything we just talked about. Stars are formed by interstellar gas coming together through gravitational attraction. Uh, the fusion process occurs when there's enough heat to start that. Um, And this is that the equilibrium we talked about between the radiation pressure pushing out and the gravitational pressure pushing in. Um, and so in most stable stars, you have the balance between those two forces. Okay, so pause there if you need to look at that some more. Okay, now if you think of a star, when we talk about fusion happening in a star, the fusion is occurring in the center of the star, in what's called the core of the star. Okay, and so before when I said the surface of a star, the surface of our sun is about 5,700 Kelvin, there's not fusion occurring at the surface. It's all happening like inside in the middle. Okay, there's also different types of stars. The more massive stars tend to be more blue. We'll talk about that later. Our sun is more of a like white yellowish kind of star, but you could also have a very low mass star, which would be like a red dwarf, and we'll talk more about that later. But there are different types of stars. Okay, now there's something called luminosity of a star. And the luminosity of a star is basically defined as the energy that the star gives off per second. Okay, so in other words, it's basically the power output of a star, and that would be measured in watts. So like, for example, you get a light bulb that could have a luminosity of 60 watts. That means it puts out 60 joules per second. Okay, compare that to the luminosity of our sun, which is way more than that. In fact, we'll see the value here in just a second. Primarily, that luminosity, that power output comes from mass. In fact, the mass of a normal star almost completely determines both its luminosity and temperature. And the reason for that is because the more mass you have, that means you have more gravitational force pulling things in. And if you have more gravitational force pulling the hydrogen in, you get higher temperatures. And if you get higher temperatures, you have, you know, a hotter star, and therefore a more luminous star because it's giving off more power. Okay, and so the mass of a star, or really I guess you could say the mass of that gas cloud that formed the star, is what determines the outcome of the star, how big it's going to be, how hot it's going to be, etc. Okay, and so this is basically what I just talked about. Okay, so mass determines luminosity. Okay, and of course, the luminosity of a star is an intrinsic property. It doesn't depend on how you measure it or on distance. For example, a 60-watt light bulb is giving off 60 joules per second. That's the same whether you're right next to the light bulb or whether you're farther away from the light bulb. Okay, so luminosity of a star is an intrinsic property. Now, the luminosity of our sun is approximately 3.9 times 10 to the 26 watts, which is a lot of power, obviously. Sometimes you see this value written with a symbol L and then a circle with a dot. I don't know exactly why they use that symbol, but sometimes you see that. You could also write like L subscript sun. Um, and basically what that means is that every second our sun emits 3.9 times 10 to the 26 joules per second in all directions. And so the energy that arrives at Earth is only a very small percentage of that power. And in fact, we've kind of talked about that before when we talked about like the solar constant in the past unit, how if you imagine all that power spread out over a sphere of surface area 4 pi r squared, that because the Earth is far away from the sun, we only get like a fraction of that total luminosity. All right, so now we're going to talk about some things that are new to us. Normally we would have talked about in topic 8, but we skipped part of topic 8. And so we're going to talk about what's called the Stefan-Boltzmann Law. Okay, so later on we're going to see what's called a radiation spectrum, but basically radiation spectrum can give us information about the luminosity of a star. Okay, and this guy, I guess his name was Stefan, helped come up with this equation, which is called the Stefan-Boltzmann law. Okay, so this equation right here is called the Stefan-Boltzmann law. L is the symbol for luminosity. Of course, that is measured in watts. This symbol right here, this is the Greek letter sigma. That's a lowercase sigma, not to be confused with an uppercase sigma, which is used in math to represent a sum. This sigma is a constant. This is known as the Stefan-Boltzmann constant. It is given to you in the data booklet, and it has a value of approximately 5.67 times 10 to the negative 8 watts per square meter per Kelvin to the fourth power. A is the surface area of the object. Okay, so if you're talking about a star, and a star is like a sphere, then that would be like 4 pi r squared. And then T is the temperature of the object measured in Kelvin. Okay, and so basically what we see from this equation is that the luminosity of a star depends on basically two factors. Number one, its temperature. Not just the temperature, but temperature raised to the fourth power. Do keep in mind that temperature does have to be in Kelvin when you're using this equation. And then A, where A is the surface area of the object. And for a star, which is like a sphere, the area of a sphere is 4 pi r squared. So in other words, the luminosity of a star depends on how hot is it and how big is it, which if you think about it, makes sense. Okay, so pause it there. Make sure you have that in your notes. There is another equation, which is going to be new to us that normally we would have talked about in 8.2, but we skipped that chapter, and that is what's called Wien's law. Okay, and so Wien's law, basically, what Wien's law does is it helps us relate the temperature of an object to the wavelength of the electromagnetic radiation emitted from that object. So let me back up. All objects in the universe emit electromagnetic radiation, okay, at all different wavelengths. Um, whether that's, our bodies, the walls in our homes, stars, any object in the universe emits some type of electromagnetic radiation. Okay, and if you were to graph that electromagnetic radiation and see like at what wavelengths are different objects emitting electromagnetic radiation, you would get a graph that looks something like this. Okay, where on the x-axis we have wavelength, and on the y-axis we have intensity. Okay, so in other words, let's say this object is like a light bulb. Okay, a light bulb emits electromagnetic radiation across the entire EM spectrum, from radio waves down to X-rays. But there is a peak wavelength where most of the radiation is emitted. Okay, you see how this graph has a peak. This peak wavelength is what we call lambda max. Okay, that is it's the highest point on this graph. That's what's called lambda max. Okay, so this is what we would call the peak wavelength. Okay, and again, you could do this graph for any object. Obviously, in this unit, we're talking about stars, and so if you think of our sun emits all types of EM radiation, right? Radio waves, infrared, visible light, ultraviolet, X-rays, okay, across the entire EM spectrum. But there is a peak wavelength where the most energy comes out at that one wavelength. What Wien's law says, okay, and this is the equation for Wien's law, basically. Wien's law basically relates that peak wavelength to the temperature of the object. Okay, in other words, if you multiply that peak wavelength in meters times the temperature of the object in Kelvin, that is equal to a constant. And the value of that constant is about 2.9 times 10 to the negative 3 meter Kelvin. Okay, so that's not millikelvin, that's meter times Kelvin. Okay, so in other words, the product of these two variables is equal to a constant, which means that if one of them goes up, the other has to go down. And so you can see from this equation, for example, if I take an object and I make it hotter, if the temperature gets bigger, that means the peak wavelength of the EM radiation emitted is going to decrease. Okay, and so we have Wien's law, which is right here, and then we have the Stefan-Boltzmann law that we saw on the last slide. Okay, so make sure you add both of those to your notes. Okay, now here is why this is useful. That peak wavelength that I talked about before is something that we can directly measure because we have equipment where we can basically point, not a camera per se, but a sensor and collect light from an object and kind of measure directly what is the peak wavelength emitted from that object. And if we can directly measure that, then we can also go back and use Vine's law to find the temperature of that object. So for example, when we look at the spectrum, when we look at the light coming from our sun, we notice that the sun emits energy with a peak wavelength of about 500 nanometers. Okay, and so if we use Vine's law and plug in 500 nanometers that you see down here, we can determine that that our sun, at least the surface of our sun, where the light comes from, has a temperature of about 5800 Kelvin. So if you ever wanted to know, like, how do we know how hot the sun is if we've never been there? Or how do we know how hot other stars are if the star is like, 20,000 light years away, how do we know how hot that star is? Well, it all has to do with the light. Okay, by analyzing the light and figuring out what does this curve look like, this is called a black body curve. By figuring out what the shape of this curve looks like and finding where the peak wavelength is, we can use Vine's law to estimate what the temperature of the object is, okay, which I always thought was pretty interesting. It's amazing the information that we can determine just by looking at the light coming off of a star. And this is only the first step, by the way. There's other information we can determine from light that we'll talk about throughout this unit. Okay, but one of those is temperature because of like I said, Vine's law. Okay, I also want to point out that here you can see three different blackbody curves. Okay, and you can actually see because of Vine's law that we talked about before, as the temperature of a star goes up, that means the peak wavelength is actually going to go down and it's going to decrease. This is also the reason, by the way, why hotter stars tend to be blue and colder stars tend to be red, because red light has a longer wavelength than blue light. And so if you take a star and you increase its temperature, then as the temperature goes up, the peak wavelength is going to shift towards the blue side of the spectrum. And so it's going to appear more blue. And so the coldest stars start off red. If you had a star that was hotter, then its peak wavelength would shift towards the middle, maybe like around orange or yellow. And if its peak wavelength like kind of overlaps the entire part of the visible spectrum, then it might be white. And if it's hot enough, like if, for example, a 15,000 Kelvin star, then the peak wavelength might be over here on the blue side. Okay, and this is also, by the way, why this is basically what I was talking about. So here you can see the blackbody curves for three different stars. This would be a star that's only 3,000 Kelvin. Okay, this would be like our sun that has a peak wavelength or a temperature of around 6,000 Kelvin, and then this would be a really hot star. Okay, and so based off of where the peak wavelength is, that determines what the star looks like. Okay, so the color of the star is determined by its temperature. I was also going to point out one reason why we don't have green stars, for example, is because let's say if the peak was in the green part of the spectrum, just because the peak is in the green part of the spectrum doesn't mean the star looks green. Because actually, if the peak is in the middle, that means all of the visible light is included. And so if you put all visible light together, you actually get white light. Okay, and so even if the peak was in the green part of the spectrum, the star wouldn't look green. Okay, that's the same reason why there's no like pink stars or purple stars. Okay, because those stars are like, or those colors are composites of other colors, and it doesn't work out based off of the shape of the blackbody curve. Okay, so that's one piece of information we can determine from what's called the spectrum of a star. Okay, we can use Vine's law to determine the temperature from its spectrum. And then if we know the temperature and we also know the luminosity, which we can kind of measure the luminosity as we'll talk about, then we can also find the radius of the star from the Stefan-Boltzmann law. Because remember, the Stefan-Boltzmann law has that 4 pi r squared in it. And so if we can determine L and we can determine T, then we can also find the radius of, of a star. Okay, and so before we get into any other calculations, I think we're going to go ahead and stop the video here. As always, please let me know if you have any questions, and I'll see you guys in the next video.